Ja. Ja. Ja.
Where can I get information? What kind of projects?
Just walk by the bike lab on a Monday. Or...
Okay.
Ja. Hoi.
Bij die volgende opdracht gaan we dan Odesolvers gebruiken of dat niet? Je moet hem gewoon opmaken.
Ik weet niet wat de volgende opdracht is.
Oh, en dan ben je numerical. Je kan hem gewoon in Odesolver gooien en dan heb je een rekening maken. Maar je... Oh,
Nee, je moet helemaal
dat is
zo.
niet op. Ja, want anders doe je van één comment en dan heb je van dat. Dat bedoel ik, dan heb ik de opdracht zo gedaan. Dus. Als je het moet integreren. Dat deden wij bij bewegingswetenschappen, maar ik neem aan dat het de bedoeling is dat je weet hoe je met de opdracht. Ja, anders ben je binnen 2 minuten klaar.
Nauwkeurigheid, foutschatten.
Oké, zo.
Komt allemaal nog. Oké, nou, dat gaat anders doen.
Ik heb een vraagje. In deze redenering, wanneer je zegt van ja, neem de adapted order om de acceleration uit te rekenen van punt B, dan neemt u de momenten om
Punt A.
op punt A, maar u neemt daarbij niet houdt geen
Nee,
rekening
alleen,
met,
ik doe even alleen als dit lichaam er alleen zou zijn.
ja.
Hoe hard valt dan?
Maar er zit normaal gesproken natuurlijk wel een reactiekracht van.
Komt nog wel, maar stel dat ze als free body vallen, dan zit hierboven ook nog een body. Ik heb het even losgeknipt. Nou, deze gaat met G, dat weet ik.
Ja.
En dan de grote vraag is, als deze free body, hè, dit zijn allebei free, hoe groot is deze versnelling hierna? Als die groter is dan G, ja, dan duwt hij hem.
Oh, zo.
Dat was het idee. Ja?
Ja, oké, duidelijk.
Oké, I somebody told me that the sound was really bad, a lot of bang, bang all the time. What I now do is I take the sound from the camera from Logitech and not from the laptop, so hopefully things are getting better. Just before the break, I wanted to show a movie from the old days, a GIF file, animated GIF file. Yes. Is it off? Oh, that screen. Yeah, sorry. It's the other screen. Yeah, thank you. So I wanted to show an animated GIF file that didn't work, but now in the browser, of course. So this is numerical integration. And with a rather coarse step size, I think I took 0.1 second. Now, what we see is that it moves as I described, that it goes like this, and the angles and the motion. But we also see that the things fly apart. And that is not good. Now, one way to solve that is of course obvious, that, yeah, you should take a smaller step size, because at this coarse step size, you make errors. But if you do that, you will see that they will still fly apart. It takes a bit longer, but... and if you then again take smaller step size, you will see that, yeah, it looks better, but after a while, it still flies apart. So apparently, we still have a problem there, although we use a good numerical integration scheme and we do the correct equations of motion. This combination of this form of constraint equation of motion and numerical integration asks for some extra attention to get the correct results in time. That's topic of lecture, I don't know, somewhere in this course. We will get to that. Let's go back to our problem. So we have shown these different positions. We understand a little bit about motion. Now, why did I do this? Just to interpret the accelerations. That was the only reason, to show, oh yeah, those numbers make sense. In homework assignment 1, we saw, what did we see? Well, here we had this matrix, a mass matrix. You had A, you had B, we had zeros here, we had accelerations here, we have constraint forces. On the right hand side we have some of the applied forces, right? And here we have, yeah, terms with x and x dot squared and whatever, I don't know. Terms. We noticed that A was B transpose, or minus B transpose. And that is sort of strange, because if you think back how you derive these things, then B was derived, how do we get the matrix B from B? Newton, the free body diagrams. From the free body diagrams we got the matrix B, because that was how do these forces, these constraint forces, act on the different bodies. And the matrix A was derived from, and that's where from the constraints, right? And the constraints were this form C of x. Oh, that is ugly. Let's do that again. So the constraints had this form as C of x is 0 from these equations. And then in particular, the derivative of the C matrix with respect to x was this A. Yeah, it can be specific. The A matrix is this dC, it's not a C, dC dx. These are both vectors, so eventually you get a matrix. And the B, just by cutting the bodies and drawing all these arrows and so on. And therefore, sometimes you get a different sign in A or B. Because, well, when you cut the bodies and you introduce a constraint force, it's up to you to say, well, the force from A to B is in the positive direction and B to A in the negative, or the other way around. So that is a sign convention. Now, having seen this, you have done too much work, and as I said, that's not what people want to do. We want to minimize work, and actually, we're going to use a sort of a principle of work or power, actually, to show that that you only have to derive one thing, and then you automatically get the other thing. And so we're going to do the systematic approach, and the systematic approach is based on virtual power, and that's beautiful because, well, power, if you have to do power, that's heavy. You need energy for that in time, and you need food, and you have to be strong and so on. But virtual power, you have to do nothing because it's all virtual. It's not real. So that's really cool, virtual power. And there is this statement about equilibrium, and we need a little bit D'Alembert forces and those kind of things. But that will merely come later. Now, what is virtual power? Virtual power is usually, we write it like this. We say virtual power is force times virtual velocity. And you can even make have vectors. Now these are scalars, force times velocity, and to be more specific, what is then the force? Well, you have here a point x, and on that point we have a force F. So it is the point of application where the force is applied, that point. And from that point you need the velocity, and then you multiply it with the force, and then you get one number, and that is the power. So maybe let's get rid of virtual, because that's already a step too far. Let's start with the real power. So this is just power. Power of a applied force. And of course you can, that holds for one scalar. Can I get an update on the sound? How is the sound in the stream? Any complaints?
I think she said that it's still, when you touch something, then she hears all the noise still.
Maybe I'm going to touch the table. Yeah, sorry. Okay, I will check at home what's going on. Okay, back to the power. So if that's one force, if it's more forces, you can just say it's the sum of. So it's the sum of I, force I times. If we have a number of forces applied on the body, then of course you have to add that up. So the thing is, power is a scalar, right? It's one number. Okay, so that's real power. Now what is virtual power? Virtual power is, for instance, this. PV is the sum of all Fi x dot IV. So it's not the real velocity, it's some virtual one. It's some velocity distribution which we at that moment want to apply. And we're sort of free to choose in that. Virtual, we can take any velocity distribution we like. And then we get some number. Now, on purpose, I didn't use that delta. And I use here a subscript, but you could also say, I should say what this is. So this is virtual power. Virtual power. Watch the V. But you could also say, oh, this is virtual power. I mean, it's all in the notation. But you say, oh, it's a bar over it. Now, to comply with literature, in literature, we usually say virtual power, we write it as delta P is the sum of all the forces applied at delta x dot I. But be aware, the D has nothing to do with differentiation. Nothing. I know nothing. Mr. Faulty, nothing. Right? So the D is not for differentiation. Neither is the D for small. There's nothing to do with smallness. The speed can be 10,000 miles per second, the virtual velocity. Doesn't matter. The D is not for small, the D is not for differentiation. It's just, yeah, the way people write it. Now we will stick to this form with a delta. Now, what is the use of this? Well, we say that the system is in equilibrium if the virtual power is 0 for all virtual velocities, virtual velocities, delta x dot y. That is a statement. So this is an important statement. Because what does it say? It tells us when is the system in equilibrium. Now, are we interested in equilibrium? Maybe, I don't know, depends. Is motion, is that equilibrium? We are actually interested in motion, right? We're not interested in equilibrium. Equilibrium is for softies. It's, you started the first year, you did statics and all those kind of things which didn't move. We're not interested in that. We want to move on. So we want to do dynamics. So we have a problem with this whole statement about equilibrium. Yeah? We want motion. Now, there's one guy who can help us with that motion, and that is D'Alembert. Because instead, D'Alembert said, well, we can, any dynamical system, any system in motion, we can look at it as a sort of a dynamic equilibrium. Because he looked at the equation, D'Alembert, a smart guy, he looked at the equation for statics. So statics, what does statics say? Sum of the forces is 0. And what does dynamics say? Well, let me see. I have this book of Newton, and it says, mass times acceleration. And then he came with a brilliant idea, D'Alembert. He said, well, I'm going to introduce a thing. It's called an inertia force. And it's minus mx double dot, and I call that the inertia force. And now I can make any dynamic problem into a static problem. Because I take that equation from Newton and I write it in a different way. I say the sum of the forces plus the inertia force is 0. And now, oh, hello Siri, go away. And then I have changed my dynamics problem into a statics problem. So now I can apply that whole idea of equilibrium. So again, with the D'Alembert forces, I can reformulate our virtual power. And I can say, oh yeah, the sum of the forces plus the inertia force times the delta x dot I, that is my virtual power. And now the game looks a bit stupid because now the following step you make, well, of course you can substitute that inertia in there. You can say the sum of these Fi's plus, no, it's a minus then of course. No? Minus, that is mi x double dot I times delta x dot is then this delta p. Why did I put the sum there? Stupid me. Now we say when is it in equilibrium, and then and I should say equilibrium, and then I write in front of it dynamic equilibrium, because we included that. When delta p is 0 for all velocities which are non-zero. Because these virtual velocities should be arbitrary, so they should be anything. Now, the game we then play is if it should hold for every virtual velocity, then we say, well, first let's take x dot 1 equal to 1 and the rest 0. So we say delta x dot 1 is 0 and the rest is 1, sorry. Is 1. 2, 2, go back. 2, 2. Equals to 1 and the rest 0. If we do that, then our delta p is 0, breaks down to f1 minus this m1 x double double. 0. And then we do the delta x dot 2 is 1 and the rest is 0, and we do this and we get f2 is minus m2, etc. So finally we get back our equation, that the force minus mi x double dot I is 0. Which looks like a stupid thing. I mean, first you have a whole set of equations, then you multiply them with 0 velocities, you add them all up, and you say, well, it's in equilibrium if I do this for arbitrary velocities. And then you put in the arbitrary velocities and you get back the equation. So it doesn't look like a very helpful scheme. But the crux is in this idea of virtual velocities. Of course, I did it a bit on a sloppy way because we have positions and orientations, so you have to take masses and mass moment of inertia, but that's not the basic idea. The basic idea is this virtual power expression. So coming back now to the virtual power expression of our system, of our constrained system. So constrained system. Then how does the virtual power expression look? Then we have this delta P. Of course, we have applied forces, which we called Fi. Then we have a mass matrix, as we have seen. The inertia forces we can write as a mass matrix times accelerations. So minus mij x double dot j, and we have to sum over j for that. Then we get all these inertia forces. So these are the applied forces minus the inertia forces. And then times, we have to do all these different velocities. And what does the xi look like? Well, x1, y1, phi1, x2, y2, phi2, etc. Until xn, yn, phi n. And the same, the mij, what is that? That's this nice diagonal matrix. And the entries are m1, m1, I1, M2, M2, I2, etc. until M, N, M, I. What more do we have to define? Oh yeah, the forces maybe. So the forces are, of course, Fx1, Fy1, M1, Fx2, Fy2, etc. until Mn. So now we have to find all our quantities. Now we say that this delta system is in equilibrium, so I should start with that. System is in dynamic equilibrium when delta P is 0 for all virtual velocities which are non-zero and which fulfill the constraints. Because now, remember, we don't have free bodies, but we have that everything is connected, our glue. So although you would think, oh yeah, for the free bodies, all those velocities are free, I can just take any velocity I want. If you have a constrained system, then not all velocity distributions fulfill the constraints. Think of the homework, the in-class quiz problem. You had a double pendulum with a lot of constraints, and you knew only one rotational velocity, and from those, by magic, you could calculate what all the velocities were. So they were just a function of one variable. They were not arbitrary. So we have to find out what is the allowable velocity distribution which fulfills these constraints. Now, to do that, we have to know what the constraints are. So we say the constraints in a general form are, and we have C of this X is 0, or in the index notation. So yeah, I'm already started to use index notation. Ci from xj is 0. And I is the number of constraints I have. And for j, I just take the number of coordinates. Should be like 3n. If I have n bodies, I have 3n coordinates. And this is the number of constraints. Can I see hands for those who are not familiar with the index notation and Einstein's summation convention? I see some hands. A very quick crash course. Until now we did use matrices and vectors, right? And everybody knows when I write this, A times X is Y, knows what I mean. Apparently there's a matrix A, there's a vector X, and there's a vector Y. Yeah? If you use index notation, you would write it like this. And then J is 1 till, well, whatever J is. I don't know, M or N. So this is index notation, but I hate writing this summation sign. So I have a shorthand form for this, and it is ijxj is. And then the unwritten rule is that the summation is always over the repeated index. So if you see a repeated index, you do summation. Yeah? And that makes life a bit simpler to write things. Then I have to tell you one more little thing, and that's differentiation. So with this index notation, if I'm going to differentiate this with respect to the coordinate, the Jacobian, so the dci of xj with respect to xj, well, that is a lot of writing with a lot of symbols, and there is a shorthand notation for that, ci, comma, j. So this comma means that I differentiate with respect to that j coordinate. With those two things, the index notation and the summation convention, and the comma for doing the differentiation, I'm able to write down in a pretty short form what all the formulas are. So let's get back with that intermezzo to our original problem. So we had this delta P, then we have the Fi minus Mij x double dot j, remember summation over the index, and then x dot I virtual. Remember summation over this I thing? Yeah. So I'm not writing it anymore, but that's the beauty. And then we have the constraints. So then the virtual velocities, they have to fulfill the constraints. And the constraints are this form, C. Well, I tend to use then a new index, Ck of x. Can still use I, is 0. K is the number of constraints we have. Now, looking at the constraints, they say nothing about the velocities. So I need velocity constraints. So what are the velocity constraints? Well, that is super easy. And to help those people who are not so familiar, I first write it in a nice form, Ck, comma, dx. Oh, that's not nice. dxi times x dot I is 0. Remember this summation, don't forget it. And actually I don't want to write it, I want to write ck, comma I, x dot I is 0. So these are now my constraints on the velocities. we clearly see CKI is like a Jacobian matrix. We have two indices times this. Now finally we can say, oh yeah, these virtual velocities, here we have real velocities, so for the virtual velocities we have to write CKI delta x dot I is 0. So these are the constraints we have to fulfill. So we are not free to take any any velocity distribution, but all velocity distributions must fulfill this equation. Now the next step is really magic. I mean, Newton was already magic, but what we're now going to do is really like, huh? Because one way to do it would say, take these equations and say it's 4 equations with 6 unknowns, and apparently there are 2 degrees of freedom, and I can subtract 2 coordinates, and I can write all the coordinates as a function of those 2 coordinates. That would be a way to go. Think of the double pendulum. You have 6 coordinates, you have 4 constraints, so apparently there are 2 degrees of freedom, which we easily identify as the 2 angles of the pendulum. Solve the problem. But it's like with having children. You don't want to have any preference for your children. And the same holds for the coordinates. So in the case of the pendulum, I choose the angles because, yeah, I think that is the right choice to do. But why not take 2 x coordinates or an x and a y coordinate or any other coordinate? So as you do in a family, no preference over one child over the other. You do the same within mechanics, no preference for any coordinate. So we're not going to make a choice. Then the way to incorporate these constraints is by using the magic Lagrange multipliers. So what we do is we incorporate this expression into our virtual power expression. So we make a new, we introduce the Lagrange multipliers. And how many? Well, as many as we have constraints. As many as we have these CKs, meaning we call them lambda k. Usually we multiply as we call them. And then what do? We multiply these lambda k's times this expression, and then we add that to our virtual power equation. So we formulate a new virtual power equation with a star. And the original one was the Fi minus the Mij x double dot j. And then we had this virtual velocity I. And now we add in a very special way. I add them with a minus sign, and that is just a sign convention. Lambda k times, and I put a bracket here to show you that we add ck I delta x. It's not nice. Oh. CKI. So we have a new expression. So this is the virtual power of the applied forces, of the inertia forces. And this is the virtual power. Yeah, how can you read this? Well, when that's nothing actually. If I fulfill the constraints, then here we have zeros. And then these lambda can be anything. They can be 123.8, because 123.8 times 0 is 0. So if we fulfill the constraints, we do not add anything. Yeah? That is the end. Now, it holds for arbitrary virtual velocities, as long as they're not 0, because the whole concept of constraint is incorporated within this virtual power one. And meaning that for every delta x dot I it should hold, so I get I equations. I equations. And the I equations are then of this form, Fi minus Mij x double dot j minus lambda k ck comma I equals 0. And these are what we call the constraint equations of motion. Now, we usually rewrite them, we write them in another form, because our unknowns are what are the unknown quantities in the the accelerations and of course these multipliers, because we have no clue what they are. I said 123.8, but maybe they're minus 25, who knows? We have to calculate. Okay, how many unknowns we have? The number of these unknowns is equal to 3 times n, the number of rigid bodies, plus m, the number of constraints we have. And how many equations do we have? Three n. So again, we have this Cole-Porter problem. We have less equations than unknowns, or in other words, we have more unknowns than equations. So what do we have to add? How do we get back to our original system? Bison kit. Glue. We need glue. There's glue. And what was the glue? The glue were our constraint equations. Ck xi is 0. And of course, we need the glue on a higher level. We need to differentiate our glue. So we need to do dt of our glue. Or in other words, I have to write it down on the acceleration level. Well, first on the speed level, that is not going well. X dot I is 0. So these are the constraints on the velocities. And now differentiate again. Cky x double dot I plus Ckij x dot I x dot j is 0. So these now are our constraints in the unknown accelerations. So, and the number of equations we have here is of course equal to m, making that this plus this one make up for the number of unknowns. Comply. So now we have enough equations and for the unknowns we have. And let's rewrite these two set of equations in our familiar form. Rewrite, combine into, and then we write it in a sort of pseudo matrix vector form, because I still hold on to my index notation. Well, the unknowns are clear, x double dot I. And the other unknowns are the Lagrange multiplier k. And then I only have to read the first equation and then put it here. And if I start with a mass, I say m, maybe I change this to j, mij times x double dot. And then I know on the right hand side I have an fi, that is correct. And these terms are unknown. So I have to keep them on this side. So I get c, k, it's the first side. And now I have to add this equation. Note that every index which I use for summation, I can change in any index I want. Because it's a dead index, it doesn't go out of the equation, it's used for summation. So instead of the I could use Fiets-Bell or bracelet or whatever. And since I choose to do a lambda k, x double dot j, I have to write here c k comma j, no, that's not nicely written, j, and this is a k, because the j from this goes with this one, like in here, and k coming out, that's okay, and then this part on this side of the equation, so we get a minus sign, ck or l m or something like that, x dot l. Now these are now the constraint equations of motion. So that is a nice result. We have, in a systematic way, derived this equation. And note that what our goal was in the beginning, remember M, A, B, 0 for the matrices, X double dot, and some other terms here, Fi and minus something, whatever. So we say A is B transpose. Oh, here we have zeros, by the way. How many? K, K. We see this whole structure back in this equation, while C, maybe I nicify this a bit, it's so ugly. C, K. How do we see from the index notation that this is the transpose of this or the other way around? That's a bit difficult to see. And the trick is the order of the indices. Because if you write down for a matrix A times X, a vector, and then you do Aij Xj. Now if you do A transpose times X, what do you have to do? You have to do Aj Xj, right? That's the transpose action. So if we do the summation over the second index, like in here, so this is like a regular summation, a regular matrix times vector. Whereas this, you see the index k is not at the end, but the index k is at the beginning. Meaning that we apparently use this guy, but then in a transpose form. So theory, just do the homework assignment 2 and you will see that they pop up like that. And they're really identical. Now what was the main benefit of this systematic approach? It's a question, Systematic approach. Yes. Yeah, tell me. Looks like magic. That's not a benefit, right? A lot of scribbling. Neither a benefit. Yeah. Yes. No more free body diagrams. Yo! That's cool. So, and don't tell Heike. We don't have to do that. We just look at our system, we count the number of bodies, we look at what type of constraints we have, we enumerate the bodies, give them coordinates, put geometry in it, write down the constraints, which is kinematics, which, I mean, that's super simple. And then you just crank on the virtual power engine with the D'Alembert forces, and shebang, you get the equation in motion. For free, without even drawing any free body diagram. That is a super advantage. Actually, we made a very big step in mechanics in this way, because in our pencil and paper method, we used diagrams, free body diagrams. We had drawings. And from drawings, from geometry, let's keep them called drawings. From drawings, we moved to this stuff, algebra. And actually, that is the name which goes by this is the founder of multibody dynamics. Does anybody know who it is? Who made this big step from drawing and comparing to algebra? Yeah, Lagrange. Lagrange wrote a wonderful book, Mécanique analytique. So that's French, and of course everybody speaks French, so I need not translate that, right? Mécanique analytique. And what did he write in his preface of the book? He wrote, on ne trouvera Point de figure dans cet ouvrage. Now, some of you may have a trouble. We have some foreign students here, not from France, so I will help them. The translation is, you will find no figures in this book. Or in proper English, no figures will be found in this book. Now, if you go to a store and you buy a book without pictures, in the spirit of Alice in Wonderland, what would you say? What is a book without pictures? That's nothing. You don't want a book without pictures, right? You always want pictures in a book. So, how can you advertise your book by saying, oh, you will find no figures in this book? But then he continues and then he says, well, until now, all mechanics was by geometrical reasoning, and you had to draw figures and make diagrams and equate one leverage to the other. And I made that pass. That is history from now on, because the only thing you have to apply here is algebra, is analytical methods. And by using these analytical methods, you can derive the equations of motion. And by such, he became the founder of the mécanique analytique, or multi-body dynamics. Later on in the course, we will talk a little bit more about Lagrange. I'll see you next week when we're going to talk about passive and active elements and impacts. Yeah, I have to be sure that everything